This video demonstrates some MATLAB simulations of GPC with constraints. The previous video then demonstrated how to construct matrix inequalities which represent constraint satisfaction over the prediction horizon for a GPC type of algorithm. And this video is going to combine those constraints with the GPC optimization in order to produce the constraint control law. MATLAB code and simulation examples will be demonstrated. Just a reminder then of the key items. The GPC performance index was introduced in chapter 2, and you remember it took this sort of form. We had a quadratic part, there it is, delta U future transposed times S times delta U future, and then we had a linear part, delta U future transposed times, and you'll notice here that this bit I've called A for convenience. So you can summarize the performance index like this. Now I've deliberately ignored the constant term because obviously that does not affect the optimization, so we don't need it here. Just in case you need them, the output predictions are given by an equation of this form here. Now the constraint inequalities were done in the previous video, and this might look a bit messy, but you do need all of this detail. You remember that the top block represented rate constraints, the middle block represented input constraints, and the bottom block represented output constraints. So clearly, if some of those constraints do not exist, you do not need the corresponding block. But the key thing is you needed to define these matrices CC, DD, DU, DDU, and DY, and those are covered in the previous video. And you can summarize these inequalities in a slightly more compact form like this, which is what we're going to do in the code. Critically, you'll notice that the right hand side depends on UK minus 1, delta U passed, and Y passed. So if we put all this together, the GPC control law is defined by this optimization here. So you're minimizing over delta U future this quadratic performance index subject to these linear inequalities. And just in case you've forgotten, there's the definitions for S and for A, and there's the definitions for the inequalities. So all we need to do is construct some MATLAB code which will implement this optimization here. So how does the code work? You'll find first of all we define the predictions, then we define the cost function parameters which depend upon those predictions, and in case you've forgotten that, I'll just go back and show you. You'll see that S depends on prediction matrix H, and this A depends on prediction matrix H, prediction matrix P, and prediction matrix Q, and in a similar way you'll see the inequalities also use P and Q and H as well as other factors. So we define the predictions, define the cost function parameters, define the constraint equation parameters, and then we set up a loop to iterate through the control law computation, which is this quadratic programming optimization, and then update the process. So the control law requires a QP, and just as a note, for now we're ignoring advanced information on the target, and you'll remember we did that in earlier chapters as well. And for the first part of this video we're going to ignore output constraints, but we'll put those back in at the end. Now the main file that you might want to look at is this file here, mpcsimulate.m. So I'm going to show you that very briefly, and hopefully the file name is obvious. There's also another file, mpcsimulate_overlay, which you might want to use from time to time. And what that does is it plots the first value of the unconstrained optimal input alongside the constrained input, just so you can compare the two in case you find that beneficial. So let's just pop to the MATLAB window temporarily and show you this file and how easily they run before we work. So first of all, MPC simulate, and you'll notice the first key command is this one here, which forms the prediction matrices. Then you've got a blocker command which forms the unconstrained control law parameters, which we won't be using here, and the S matrix, and then there's matrix X, and if you're wondering what X is, it basically quantifies the affine term, because you can see we've got delta U future times 2 times X times DU past, Y past, and R future. So we need that X that defines our cost parameters. If we then go down, some of this is bookkeeping, so let's not worry about that. Then you find there's a block of code which finds the constraint inequalities CC, DD and DU, exactly as defined in this video, and you'll see there's the inequalities we're trying to satisfy. No output constraints here, just input rates and inputs. And then finally, this is all bookkeeping, so don't worry too much about that. You'll find we start the simulation here, and we've got the unconstrained control law up here just in case you want to see what it is. But the key thing is the quadratic programming. So if you look at these two lines, you'll notice they define the quadratic programming problem you're going to do. There's the linear inequalities, there's the performance index, and so what we need to do is find the bit in the linear inequalities which changes with time, so that's that equation there, dd plus du times u passed, and you'll see we discussed that. So exactly as in these videos, that's how the code does it. And then for the performance index, we need to calculate this term here, and you'll see that matches what we've got up here as the performance index. And then you'll notice we simply put into quadprog our S, our F, which we've just calculated, our CC, and our DT. So we simply put the numbers in exactly as we've indicated, and that gives us our constrained optimal. Now, there are a number of examples. I'm not going to run them real time because you can do that yourself, but if we look, for example, video 5.4 example 1, which we're going to talk about in a minute, you'll see at the very bottom it's got this file mpc_simulate. Now overlays the same as simulate apart from adding an extra plot, which is why I'm not going to show it. So I can just run this file by pressing F5 and it produces some figures. And you can do the same with all these others. You'll see we've got example 2 and example 3 and so on down. So wherever the examples are, if you want to run the code, you'll see there's a transparent definition. We've got model parameters, we've got choice of horizons, choice of weights, choice of constraints, target, disturbance, noise, and then simulate. So you can change these if you want, and you can reproduce the examples if you want to. So let's go and look at the first example. First example, video 5.4, example 1. And this is just demonstrating that if you use the QP, you get a different result to if you don't use the QP. So clearly the unconstrained, these dotted lines, are not the same as this solid line. The unconstrained, the dotted lines, are not the same as the solid line. So it demonstrates clearly that even for a simple tracking problem, as shown here, the constrained solution is not the same as the unconstrained. This second example has got slightly more challenging dynamics because it's got this non-minimum phase characteristic, and here what you can see is the difference between the constrained and the unconstrained is quite marked, and this would be an example where doing the constraints properly could be quite important. Now the irony here is you're looking at this and you're saying I can't see any of the inputs actually getting up to the constraint values. Why is that? Well, what you'll find is it comes down to the receding horizon concept. Because we've got a limited control horizon, the algorithm says within the control horizon this is the best I can do, and then you get another degree of freedom and it keeps updating. So the constraint violation expected or might never happen in simple terms, but I'm not going to dwell on that. Example 3. Now this is a multivariable example, so there's 3 loops, and you can see this is showing loop 1, and again you'll see the QP ensures that you meet constraints. This is loop 2, I'm sorry I didn't do the plot very well there, but you'll see the same issue, and this is loop 3, and you'll see we ensure we meet constraints down here. So that's another example for you to look at, but the bottom line here is all of these we've emphasized that the constrained and unconstrained results are different, and you can run these by yourself if you want to test it, or change the parameters, change the weights, change the target, change the limits, whatever it is you want to do. What am I going to do now? I'm going to add in some output constraints. Now just a bit of a warning here for you. When you include output constraints, you can sometimes get infeasibility. That means it's not possible to simultaneously solve all the input constraints and the output constraints. Now the code we're providing here is not designed to be robust. Basically, we've tried to keep it as simple and transparent as possible so that you can read it and see what's going on. And as a consequence, it's not robust and it's not got logic to deal with lots of different scenarios. So please accept it as it's written. The key file here that we're going to use is this one, mpc simulate _ output constraints. And the only difference between that and the earlier file is, of course, it adds an extra couple of lines which put in the output constraints. So here's a first example, video 5.4, example 4. Now we're going to show this one real time just to demonstrate a key point. You can see that here the output constraints have not been satisfied. They've clearly gone way beyond the upper limit marked on the graph. If it's not obvious, these dashed lines are the limits that you've applied. You can see that input constraints have been satisfied. So why is this, and what can we do about it? Now, first of all, what's caused this problem is we've introduced a large disturbance here. And in essence, what the system has said is, I am not feasible. Because of this large disturbance, I simply cannot satisfy the output constraints at this time here. It's too difficult. I can satisfy the input constraints, well, I've got to, I have no choice, but I cannot satisfy the output constraints. So what it's done is ignored the output constraints where it cannot satisfy them to ensure we get a sensible optimization. So if I go to the code here and demonstrate, so that was video 5.4 example 4, and if I just run this one, now you can see the plots there, but what you can't see is the warning messages. And if you go to the MATLAB window, what do you notice here? It gives you a message ignoring output constraints at sample 21 all the way down to sample 33. So in essence, it's telling you that at each of these samples the optimization was infeasible, it was not able to meet output constraints, so it's ignored them. Let's carry on then. Example 5. This one, we've not made the disturbance quite so aggressive so that you can meet the output constraint. So what you'll see is here the output constraint is active. That's caused by this disturbance. And critically, you'll notice that the difference between the constrained and the unconstrained inputs. So even though the inputs aren't near their limits, they have been changed to ensure that the output does not violate its limit. So you can see that the constraint optimization is doing its job. Whatever limit is active, that limit is having an impact and it's changing the proposed trajectories as you expect. Example 6. Now this example is quite interesting. What we've done is we've chosen, in case you haven't noticed, a non-minimum phase example. But then what we've done is we've added a fairly challenging lower constraint on the output. We said I don't want the output to go below a certain point. And you can see that constraint has had a huge impact on what happens with the constrained inputs as opposed to the unconstrained inputs. So in order to satisfy the output constraints, I've got quite a serious impact on performance, and in essence you can see this is very slow to respond. Now what I can do is I can actually add a more challenging output limit. So that output limit is bad enough. What happens if I add an even more challenging one? So if you look at this example, where's the output limit now? You can see the output limit is only just below 0. And as a consequence, in order to meet that constraint, I've really had a big sacrifice to what I can do with my inputs, and the performance is very, very slow. But the key thing is I have met the constraints. So the QP works. It ensures that I meet the constraints as required. Now the fact that you might say this is unrealistic isn't the point. What we're trying to do is demonstrate here that if you add constraints into the predictive control law, it will deal with them and it will do the best that it can within that scenario. And finally, example 7, just putting some output constraints in here, and you'll notice again we've got these sizable disturbances just to upset things, and when that sizable disturbance happens, temporarily we cannot meet the output constraints and therefore they will be ignored. And if you look in the MATLAB window, you'll see it comes up with a warning flag to say ignoring output constraints. You'll notice, however, again, if you look at these plots, that overall input constraints are satisfied. There's a difference between the constrained and the unconstrained, as you expected. The algorithm is doing exactly as you expect. So in summary, the video has demonstrated the MATLAB code for implementing a constrained GPC control law. It's shown how the QP proposes only control strategies which satisfy constraints, and consequently, assuming sensible choices for the horizons, it will give you good behavior. The code is all on the GPC folder should you want to look at it and run it yourself. We've assumed no advanced information on the target for now because that mixes concepts up. And we've warned you that at times you cannot satisfy output and input constraints simultaneously, especially where, for example, there's a large disturbance. And the code we've provided here simply ignores the output constraints in that scenario. We're not necessarily saying that's the best thing to do, but it's a simple solution to keep the code simple for now.